Okay, so we're doing hypothesis testing about the mean. It's basically the same thing as the proportion. Everything's the same except for now we're looking at a means instead of looking at proportions. Um, there is a little bit of a difference. So with if you know, so there's two possibilities. If you know the population standard deviation, which doesn't happen that often, but can happen. If you know that the standard deviation of the population, which is sigma, then you use what's called a z-test. If you do not know that, then you use what's called a t-test, which is the student t-test, which is what I talked about with regard to William Gossett from the Guinness Brewery in the last couple of videos that I did. We are going to use the t-test quite a bit. We'll use t-intervals and things like that as well. And so do not be surprised if we're using a t-test more often than a z-test. It all depends on if we know what sigma is and if we don't know what sigma is. If we know sigma, we use z. If we don't know sigma, then we use t. Okay. So here's some more formulas. Notice they're talking about n minus 1 degrees of freedom. Have to keep that in mind. We probably won't have to use that often because that's more when you're using the t-tables. In the homework, I will have you do that once or twice, but we're mainly going to use we're mainly going to use the TI-84. And when we use the TI-84, you get the p-value, and you just compare it to alpha, and we won't have to compute any critical values or anything like that. Okay. So the t-distribution is different for different degrees of freedom. We know that because that's why that table has so many different levels. It's got so many different values. Each one represents a different different degree of freedom. T distribution centered at 0 and is symmetric about 0, so that happens. We talked about this already. We know it's 1/2 on each side of 0. We've talked about that. As t increases or decreases without bound, the graph approaches but never equals 0. Okay, so farther left, farther right, it gets close to 0, it's an asymptote. So the area and the tails of the t-distribution are a little greater than the area and the tails of the normal distribution because using S as an estimate of sigma introduces more variability to the test statistics, to the t statistic. As the sample size in n increases, the density curve gets closer to the standard deviation of the normal density curve. So the bigger the bigger the sample, the more closely it resembles the population. Okay. We talked about that before. Testing hypotheses regarding the population mean. Same things happen. If n is greater than 30, we want to use the t-test. That's another thing. You want to use t-test if it's a big sample. Otherwise, you can probably assume it's normal anyway. What else? So, determine the null and alternative hypotheses. Again, the hypothesis, same thing, guys. These are all the same. It's just instead of using p and p hat like we were earlier, we're using mu because we're testing about the mean. Since the significance level is alpha still, that doesn't change. This is the formula for T naught. Since we're going to do this by calculator, that's not so useful to us. So we've got two-tailed tests. You can have those happen. T alpha over 2 and negative T alpha over 2. You got negative T alpha, positive T alpha. It's helpful to draw the region just because it'll help you decide if it's an upper or lower bound, which you do need to do need to know for entering it into the calculator. Actually, no, you don't need to know that for T, so never mind. P approach. Okay, these are basically the same slides as earlier, just talking about P with regard to the mean this time instead when T scores. We're going to be using the TI-83 and TI-84. If P is less than alpha, we reject the null. P is greater than alpha, we fail to reject the null. The procedure is robust, which means there's minor departures from normality will not adversely affect the results of the test. However, for small samples, if the data have outliers, procedures should not be used. So typically we'll get rid of outliers if that happens. So assume the metabolic rate of a healthy males is this, 5710 kilojoules per day. Researchers measured the RMR of 45 healthy male adults and who were listening to calm classical music and found it to be 5,708.07 with a standard deviation of 992.05. At the significance level of 0.05, is there evidence to conclude that mean RMR of males listening to calm music is different than 5,710? So this would be your not equal to, this would be your two-tailed test, because it says it's different, it doesn't specify greater than or less than. Okay, so since the sample is large, we follow the steps using the t. We're going to use the t distribution. So notice they use the not equal to, that's what I just mentioned. X bar is going to be your sample mean, S is going to be your sample standard deviation that was given to us. And they did all this, we'll put that in the calculator, and we'll put the not equal to, and it should allow us to do this. Since it's two-tailed, they're going to end up multiplying by 2, I believe. But we don't do that because we don't need to. Since the test statistic, actually no. Oh, they're doing t-test, so they're going to get their t-value and do that. So yeah, this is where they're going to multiply by 2. They do 2 times this, the p-value, that's what I was referring to when I said they're going to multiply by 2. You don't have to do that for the z-scores or t-scores. So the t-value they got was where is it? Oh, it's t is 0.013, so times that by 2, that's 0.026. And so, or is it not? What am I looking at? They didn't put the actual p-value then, I guess. Oh, okay. I guess they didn't put the p-value. So they're just okay. So this is not the. I thought that was the p-value. It's not. It's the t-value at that point. So when they got the p-value, it must have been some value that when you times it by 2, it's greater than 0.5. So there is insufficient evidence to conclude. So all that means is that p was greater than alpha, and so there's insufficient evidence to conclude that listening to the music will make the amount of kilojoules per day different from 5710, okay, which was the original null hypothesis. So they'll also do things like give you a list, and they'll give you values, and if you're using the TI-84 or 3, you can enter those into a list, and you can use those values to do this test. Instead of using statistics, you'll use, I forget what it's called. It's let me look real quick. It is called data. So it'll accept data, and it'll use this data that's given to you to do this stuff. So you go ahead and enter it, and you can kind of look at this. They want you to text and make sure that this is sort of linear. If it is, then it's considered normal, so you can actually do the test. They give you some data to check if there's outliers, which is good practice. This is the t-values. Did they do the p-value? Yeah, they do the p-value. And p-value is less than 0.02, which I think is the alpha. Is that what they use? What did they use for alpha? Oh, no. Yeah. Hold on. Sorry. Since alpha is 0.05, if they got 0.02, then that would mean that p was less than alpha. And so you'd reject the null and you'd accept whatever the hypothesis was and you'd move on. So when a large sample size is used in a hypothesis test, the result could be statistically significant, even though the difference between the sample statistic and mean statistic in the null hypothesis may have no practical significance. Practical significance refers to the idea that while small differences between statistical and parameter state between the statistic and parameter stated in the null hypothesis are statistically significant, the difference may not be large enough to cause concern or be considered important. So in this statistical versus practical significance. In 2003, the average age of a mother at the time of her first childbirth was 25.2. To determine the average age has increased, a random sample of 1,200 mothers is taken and is found to have a sample mean age of 25.5 with a standard deviation of 4.8. Determine whether the mean age has increased using the significance level of alpha equals 0.05. So they do a hypothesis test. Since it's right-tailed, the critical value with this, here we go, they've got all this. P is less than 0.025. Because P is less than the level of significance of 0.05, we reject the null. Therefore, there's sufficient evidence at the 0.05 significance level to conclude that the mean age of a mother at the time of her first childbirth is greater than 25.2. Although we found the difference in age to be significant, there is no practical significance in the age. So it doesn't really matter that that's 25.2. For large sample sizes can lead to statistically significant results, while the difference between the statistics and parameter is not enough to be considered practically significant. And that is that for this section. We'll talk about these momentarily, but we're going to go and do some homework and get you guys using the calculator to solve some hypothesis tests. Thanks.